So we have the question: a particle of mass 10 gram moves in a line with retardation 2x, where x is the displacement in SI units. Its loss of kinetic energy for the above displacement is. So this is one such question where well, I see most of the students, and especially when we do this question in the exam, exam pressure, we often tend to get confused with this negative sign, with the convention of loss and retardation, the sign convention. We're always confused, should we take vector approach or the scalar approach? See, no matter which approach you choose, you will have to arrive at the same answer. Okay, so let me just take some time to explain that here, so that you don't so that you get used to use these confusing notations at time. So it's given to us that retardation is 2x. Now, when we say retardation is 2x, it means that acceleration is equal to, right? It means acceleration is equal to minus 2x. So, to have acceleration is equal to minus 2x, I have written it as minus a is equal to 2x in both cases. Okay. Now, I'm not going to use vector approach here, but let us focus only on the scalar approach. Why? Why? Because kinetic energy is scalar. Work done is scalar, not vector. So we're not going to the vector approach. So we have minus a is equal to 2x. Now coming to the next point here, which is loss of kinetic energy. See, what is loss of kinetic energy? Change in kinetic energy is delta K. Let me just try to explain you that first. So what is change in kinetic energy? Or maybe like this. What is change in kinetic energy? Change in kinetic energy is nothing but kinetic energy final minus kinetic energy initial. And this change in kinetic energy can give you two possible values. One, it could be positive, the other, it could be negative. And if that value, right, and if that value is positive, we have that change in kinetic energy is equal to positive, implies it is a gain in kinetic energy. And maybe, so if change in kinetic energy is positive, it implies there's a gain in kinetic energy, which means velocity of the body is increasing. And if change in kinetic energy is negative, it means there is a loss in kinetic energy, which means the velocity of the body is decreasing. Okay, I hope this much is clear. We'll have detailed calculations, and then you'll understand it better. But as of now, just make a note of this. Now please do write along with me so that things become really clear to you. Now, by work energy theorem, we have work done by what? Now, I've been trying to say this almost every question, that whenever you say work energy theorem, you need to mention which kind of work is being done, or to be more precise, work is done by which kind of force. Is it a conservative force? It is a non-conservative force? Is it gravity? Is it friction? You need to mention the specified force. And since in this question there is no specific mention of the force, we assume that the only force acting here is the retarding force, and therefore I've written that work done by the retarding force should be equal to the change in kinetic energy, which could be either loss in kinetic energy or gain in kinetic energy. Now, since it is retardation here, definitely this change in kinetic energy has to be loss or negative. So what is work done? It is F dot dx. What is F? ma. What is a here? Minus 2x. So I've taken minus m outside. Okay, outside the integral. So now I can write here that minus m into integral a dx. What is a? A is minus 2x. So I have taken a, instead of writing it is minus 2x here, I already taken the minus outside. It is 2x now. So what is integral here? Upper limit is x, lower limit is 0. Integral of 2x is x square. Applying upper limit, x square at x is x square. X square at 0 is 0 square. X square minus 0 square is x square. Now we have delta K is equal to, right? So what is this? All of this is delta Ke is equal to, what is this? This is delta Ke is equal to minus 0.01 into x square. Now it is given to us in the question that the loss in kinetic energy is, it is not the change in kinetic energy. What is given to us? It is given to us that the loss in kinetic energy is equal to x upon 10 to the whole power n, right? So we have not been given change in kinetic energy. What we've been given? loss in kinetic energy. So loss in kinetic energy, this is where the point comes. Yeah. So if we say loss in kinetic energy is given to us, then what is that we have? We have is negative delta K. If gain was given, it would be positive delta K. And that is why when we say since loss is given, this value will be equal to not negative, it will be equal to positive. Okay. Why? Because loss is equal to negative delta K. Let me just write it down one more time here. So what is loss in K is equal to? Loss in K is equal to negative delta K, right? Or maybe we can write it like this. Loss in K is when Ke is equal to a negative value. Okay. So I hope that portion is clear. Now we have, if we just arrange 0.01 as 1 by 10 square, right? Because 0.01 is 1 by 100, 1 by 10 square. You can compare this value here. N is 2 and LH is x to the power n, RHS is x to the power 2, so n has to be 2. Other way around, 10 to the power n, 10 to the power 2, again n is 2. Okay. So yeah. So that's what we have here. Now, if you have any confusion here, I can just give you an example in the meanwhile, you can just make a note of this complete portion. I'll just explain you this portion also. So we have a final initial velocity as 3, final velocity of as 1 meter per second. So what is change in kinetic energy? Change in kinetic half into m into final velocity square minus initial velocity square. So it is 1 minus 9, which is minus 8. So now we have change in kinetic energy is equal to minus 8. And what does it imply? When change in kinetic energy is minus 8, it implies that loss of kinetic energy is equal to 8. And that's how we come to this plus sign here. So I hope the scalar approach is clear to you, and I hope that there's no confusion regarding this adoption of sign and conventions. Okay. So yes, now let's move on to the next question.